Hello!
Hello. I'm going to scare the audience, okay? Hello, Eric. Ryan, Mr. Eric, Mr. Ryan, how are you today?
Yeah?
Good. So, what did we talk about yesterday?
The same leaves.
Same leaves, yes.
Depth first search.
Yeah, well done. Look, depth first search, yeah? Depth first search.
Today should be breakfast. Please thumbs up on this video.
Yeah. Thumbs up. Yes, you thumbs up. Give a thumbs up, okay?
So
Depth
today
first
we're
search.
talking about breakfast search.
Same leaves. Okay, look. Look, this is a binary tree, yeah? So the leaves are on the level 1, so we should return true, yeah?
Yeah.
And how about these? The leaves are on level 1 and level 2, so we should return false. False! Remember yesterday we talked about depth first search. So basically we go down the tree and then the DFS search, remember depth DFS with the root and then the current depth, yeah? When it goes down to the next level, we increment the depth plus 1, right?
Yeah.
So, and then when we reach the leaf node, how do we check if the node is a leaf node?
Is a node that doesn't have any child.
Yeah, so root left is none, right? Yeah? And root right is none, okay? So that's the way to check if a node is a leaf node. When we reach the leaf node, we push the current, the depth of the node, the leaf node into a set, right? And then we finally check if the set contains only one element, because if it's only one element, it means what? All the leaves are on the same level, am I right?
Yeah.
Yeah, okay. So do you still remember breakfast search? So what's breakfast search? We travel the nodes level by level, yeah? So here, and then here, and here. And do you still remember how we do it? Look, this is 1, that's 2, that's 3, and that's 4. So if a binary tree is like that, so what kind of data structure we need to use in order to perform a breakfast search? What kind of data structure do you still remember? First in, first
out.
What's that?
Q.
Yeah, first in, first out, Q. Okay, first in, first out. So how do we perform this? Look, we have a Q, yeah? This is Q. First of all, it's nothing, yeah? It's nothing. Now, I'm root.
Why did it have 1?
Yeah, because I'm going to put the elements in it. Look, 1, yeah? Well, I'm here, root, yeah?
Yeah.
Root. So,
P.
so first of all, I put a root. First of all, I put the first in, yeah? Yeah, because at the beginning, I put the first root in, okay? And then, what's the Q? This is the beginning of the Q, yeah? Ryan, this is the beginning of Q, yeah? Now, I do this to Q. The Q is take the element from the Q, which is the beginning of Q, yeah?
Yeah.
Which is 1, yeah? I take it out.
Why?
Okay, I take it out because I the Q, and then what's the children of the 1?
2 and 3.
Okay, so then I put a Q here, 2, 3. Okay? Okay?
3 is a leaf.
Look. Yes, 3 is the leaf. And then I should put a level, which is 1. Yeah, it's level 1 in the set. Okay? This is 1 here. 2. Now, the next item to take out from the Q is what?
2.
2. Okay. I take it out. What's the triad of the
4.
4? And I put it here, right? Enter the Q is at the end of Q, yeah? Okay?
Line 2.
Yeah. 4 and line 2 here. Okay? So now look, what's the next is 3, yeah? Yeah? But it doesn't have anything to add. That's fine. And what's the next element? 4. It doesn't. So you should get it. Do you see how we use the Q? So we take a triad from the Q, which is at the beginning of Q. We push each kit into the Q. And meanwhile, we check if the Q is the leaf node or not. We visit the node. If it's the leaf node, we push the level. Okay?
Yeah.
So the most important thing here is that we need to carry over the depth. So look, this is root 1. We need to put a 0. The second element, tuple, so to say it's depth 0. And then when we take it out, we push it kit. Now we know the next depth is 1, right? Because 0 plus 1, right?
Yeah.
So when we deal with the leaf node, we know exactly what depth it is. Okay, so first in first out, and then the queue. Do you know in Python what can we do? What kind of data structure we can use to implement a queue? A list, yeah. Yeah, this is a list, yeah. You can use the look queue equals list, and then you can queue dot pop 0, right? But this is not O1 constant because it is a list. So a better way is to use this queue dot dequeue. What's dequeue? Double-ended queue. So this one, because then you can say queue dot pop left. Yeah, this is O1 constant. This is faster. Okay.
Yeah.
Okay. So now I'm going to write it. Okay. Should be fast. Define. Check. Let's just do maybe same. Okay. Same.
It's been 6 minutes.
Same. Okay. Then root. Okay. If root is none, if len tree is none, we can return true or false. It doesn't matter. Okay. It's a very special case. Okay. Let's return true because all the leaf nodes, no leaves are on a certain level. Okay. You can say it's true, right? Yes. Okay. Now Q equals dequeue. Yeah. Dequeue, and then I can take the parameters. I put a root node in that. So this parameter takes a list, enumerable. So I put a list and then put a root. Okay. So now the list, the queue contains only one element, which is root. Okay. Yes. And then I need to check why. Okay. Length queue. Why there's element in the queue? Right? Why there's element in the queue? Right?
Yeah.
Length is to count how many elements in the queue. Then I need to take one element from the beginning. So how do we do it? What element in the beginning? P. Let's do it P. Okay. Equals Q dot what? Remember what did I just say?
Q
The pop.
Pop.
I said pop.
Pop left. Yeah.
Yeah, I said pop.
Okay. Remember we are missing something, which is we need to put the depth in it. So instead of single element, we can do this, a tuple. Root 0, okay? And then do this.
And
Okay, so now we put the element from the beginning, yeah? And we also need a set, yeah? Let's do a set. Let's remove this, okay? Let's remove this.
What?
A special case, that doesn't matter. Okay, let's set D equals set. This is to store the depth value, okay, of the leaf nodes. Look now P is the P0 is the root and P1 is the depth, right? So if P0 dot left is none, right? And P0 dot right is none. So what does it mean? It's a leaf node, right? Am I right? Yes? Am I right? So now we need to push this one. So P1, D dot add P1, right? Okay? D dot add P1. So means that when P0 is a leaf node, P0 is the leaf node, we push the depth into the set, right? And then that's it. And if P0 dot left is not none, then we need to push it into the queue. So Q dot append what? P0 dot left and then P1 plus 1, right? P1 is the depth plus 1. And the same as this one. This is P0 dot right. And at the end we need to return what? Return. This is the same as yesterday. Do you still remember? Return what? What do you return at the end?
Length.
Length,
D.
yes?
Oh yeah.
Yeah, length.
D next.
Yeah? Length
Equals
D.
one.
Equals
Yeah.
equals. Do you mean?
I said equals 1.
Equals
Length.
Do you mean?
equal what?
Do you mean?
So this you see. So look, this P you can say P0, P1, which is you can still look because this one return the tuple. You can also have this current, comma, depth equals Q dot pop left. Okay.
Yeah.
So in this case, these values will be zip it into 2. So current will be the P0 and depth will be P1. Yeah, this is the one thing. Okay. Yeah. Okay. So now, can you tell me if there anything we can improve? Look here. Can we check, Eric? Can we check here when we adding a number into a set? We know how many numbers are in the set, right? Yeah. So can we check if the length D? Look, Eric.
Yeah.
If I added, okay, if I added this.
What?
Here, right? D dot add, yeah? If I added something here. If I said if length D bigger than 1, return false. Can I do it?
Yeah.
Yeah, because here, if I found there are already more than 2 elements, more than 1 element in the set, you'll be returned as 4 anyway, right? Yeah, because we are adding the numbers into the set. We are not taking away from it, right? The set can only grow, right? Right? Am I right? Yes? Okay, so now, what should I change the return what? Look, here return the false and here should return what?
2.
2. Yeah, well done, yes, return 2.
Ow!
Do you see it? Do you see it?
Yeah.
Do you see it? Do you understand? Look, because our target is to check if there are only 1 element in the D, right? Right?
Yeah.
And now, in this case, when we add it, we found out that if it's already more than 1, so there's no need to continue, right? We can just return false. Yeah? Do you get it?
Yeah.
Okay. Okay, so what's the term complexity?
N.
Oh, N, yeah, well done.
Mm.
Oh, N. What's the space complexity? Do we use the additional space?
I won.
Yes. No.
Yes.
I won.
N.
Oh, and because the Q, look, and the set, yeah? But set is, if we're using this, it doesn't contain more than an element, because once it's more than 1, we just quit. Yeah? Yeah. Do you get it?
Yeah.
Okay? So now I'm going to close your eyes, I'm going to erase some of it, okay?
Blah blah blah. Blah blah blah.
And
Hello. Hello.
and here. Okay.
The book.
Okay. Now do it.
E.
Right here.
Okay. So E D.
What, Ryan? Ryan, not good.
Cause.
Wow, what's the data structure?
Set.
Yeah. Okay. Right. Ryan. Okay, Eric, you have the Ryan. Okay. D dot set. Okay, well done.
Seed.
Okay, and then what's this? What's here?
The
The first statement. We want to take away from the first element from the Q. So what's it? What's it?
Q.
Q what?
The pop.
Yeah. Q P dot P equals Q dot
Dot.
P equal. No, write it properly. P equals what? We are taking 1 element from the Q at the beginning. So what's that? What's that?
P. Dot pop.
P equals Q dot what?
Pop.
Pop what?
Left.
Yeah. Got it?
Yeah.
Okay.
How do you turn this off?
That's it.
How do you turn this?
No, we don't need to turn it off. Okay, that's it for today. Good job. Good job.